Hello, my dear students. How are you? I hope you are enjoying these sessions. So today we are going to start the new session or a new chapter. In the last session, I hope you have completed the magnetism part completely. Now we are going to start a new thing that is called as a electromagnetic induction. Okay, which is the second part of a magnetism basically, but we will take it as a separate chapter, that is electromagnetic induction, which is termed or it is known as EMI. Most of you have known it as a EMI, electromagnetic induction. Okay, this is our new chapter. Before going to that chapter, I hope everyone know about C. This is as we go move further in the chapters, as we are going move ahead in the chapters, in the syllabus also. You have to remember all the previous things because that is very important. So before going to start this chapter, you should know about the magnetic flux, and I have told you what is magnetic flux. If you electric flux, I hope everyone know about the electric flux. See, what is magnetic flux? If you know about the electric flux, you can tell me about the magnetic flux also. See, according to the, that is, magnetic flux is simply defined as integral B dot ds. Okay, integral B dot ds, that is called as a magnetic flux phi. Remember, I am not putting closed integration. Why? Because if you remember, suppose I have some closed surface. This is a closed surface. Okay, this is a closed surface, and suppose the magnetic field lines are inside. Okay, magnetic field lines are inside. Correct? This is my magnetic field. Now, as you know, that is very important thing, that the magnetic field lines always exist in the closed loop. So I can say whatever the number of field lines are entering in the surface, the same number of magnetic field lines are coming out of the surface also. So the magnetic flux, total magnetic flux, will be always zero. First, what is magnetic flux? It is a simply like electric flux. What is a magnetic flux? Same thing as electric flux. Exactly same as electric flux. Just replace, okay, just replace E by B. Okay, that is a magnetic flux. Simply you replace E by B. Okay, now regarding B, we have learned about the how to calculate B for the different geometry in the last chapter. This we know, correct? This we know in magnetism. In magnetism we have learned about this, correct? I hope everyone agree with this. In electrostats we know about this. What is area vector? In electrostatic we know about this. So that's why I mentioned that why I have taken so much time to cover the electrostat, because a lot of concept which is going to be used in the further topics are going to be taught in the electrostats only. Okay, so if it is a closed surface and if it is a B, we know that it always form a closed loop. It always exists in the closed loop. Okay, it always exists in the closed loop. So as B exists in closed loop, it have same number of magnetic field lines entering and leaving the surface. So same number of magnetic field lines are entering as well as leaving the surface. So if I will calculate phi net, it will be 0. Okay, so that's why we are not calculating the closed surface. So suppose that means what I can say, from here, I can say one thing from here. If you are able to understand from here, I can say the closed integration of d dot ds, it doesn't matter, it will be always 0. This is always true. This is always true, means this thing is always 0, and that is something called as a Gauss law in magnetostats. This is called as a Gauss law in magnetostatics. Gauss law in magnetostatics. Okay, this is called as a Gauss law in magnetostatics. So that is the thing. Now, but we have to use this formula to calculate. This is the rule. But when it comes for the calculation, we have to use this formula to do the calculation. Like integration of B dot ds should be equal to the magnetic flux, and the unit will be, what is the unit? The unit is given as Weber. This is the SI unit, which is called as a Weber. Weber is a SI unit. Okay. CGS unit is Maxwell, but no need to remember that. Just you remember Weber. Okay. And from here, if we write the unit of B, the unit of B will be something called Weber divided by meter square, Weber per meter square. That is also a unit of magnetic field. Sometime you will find. So this is the about the magnetic flux. Okay, so I hope you understand the thing, like what is exactly the magnetic flux is, and what is the importance of the magnetic flux. Okay, and what is the rule for the magnetic flux. We have to calculate by using this formula, not by this, because closed integration will be always 0. Why? Because the number of magnetic field lines entering any closed surface and leaving any closed surface will be always 0. It will be always 0. Okay, it doesn't matter where it is going to be something happened or not, but it will be always 0. Clear? That is the thing. So I hope you know about in the last chapter we know about the magnetic field, we know about the area, so we can calculate the magnetic flux for any case. Let us see some example, but that is not required, but just for your for practice, we can take some example. For example, suppose we can take some surface. Suppose we take some surface. Okay. Suppose we take some surface. Suppose the magnetic field is there. The magnetic field is B naught. Okay. And suppose the radius is R. And if I ask you what is the magnetic flux, it's very simple. What is the formula? Integration of B dot ds. Okay. So magnetic field is B naught. What is the area? Area is pi r square into cos 0 degree. Okay. So this will be B naught pi r square. Someone will take 180 degree. It doesn't matter. The value will be same. Only the difference is the sign. Okay. That is a simple thing. Or you can take some other example, like what is the other case you can take? Suppose there is a wire, infinite long wire. The current is I. Okay. And suppose we have a square loop which is placed here, and this distance is suppose L, and this distance is suppose A. You have to find the flux in it, inside. What is the flux inside this? Now this is very important thing is we can say, yes, the magnetic field is not constant. So for here to calculate the magnetic flux, what we will do, what will be our approach? Our approach is to very simple. What is the approach? First you try to solve it, then I will solve it. You have to calculate the magnetic flux for this. Okay, we are taking the examples for magnetic flux, phi net calculations. So you have to do the calculation of phi net in all the questions. Okay, so just calculate the flux for net magnetic flux from this square loop. What is a net magnetic flux? Just use your brain. This is a normal simple integration question. We have seen a lot of questions on these type of things. So just use it and tell me what is the magnetic flux. What you have to do, See, the magnetic field is not constant, correct? Magnetic field is varying, so we will take a we will go from a distance x, and we will take a small element, correct? And this is dx, thickness is dx, and we will write the magnetic field. See, the flux will be d phi, small d phi will be is equal to integration of b dot ds, correct? And this will be how much? B is mu naught I upon 2 pi, correct, into what is the like area will be this length a into dx, correct? Integration, what is the integration? Integration is from L to a plus L. So when you integrate, what you will get? Mu naught I into a divided by 2 pi into ln a plus L divided by a. Okay, this is the answer, correct? Any doubt here? Clear now? So this is how you can calculate the magnetic flux. We can take a lot of examples. I have taken these two illustrations. You can take another illustration, any other type of illustration if you want, you can take. Let us for mathematics point of view, you can take any complicated example and you can do, but these are the some example you can calculate the flux. Clear? And anything else? No. So this is about the magnetic flux. Okay, so I hope you understand about the magnetic flux. So what you have to basically remember, magnetic flux is nothing, it is a something defined as a similar to that of electric flux, but only the difference is the count of the number of electric magnetic field lines. Simple, that is a simple thing. Just a minute. Yeah, so this is about the magnetic flux. I hope you have enjoyed this session and you have learned about the magnetic flux. In the next session we will learn about the EMI, that how from where the magnetic flux is changes into the current induced. Okay, that we will learn in the next session. Till then, take care, goodbye, and if you like this session, please like it, share it and subscribe it. Have a nice day. Thank you.